Hi everyone, welcome to today's webinar. We will be recording the webinar and it will be available afterwards. Please feel free to ask questions in the Q&A tab. We will be answering them throughout the webinar. Let me start by introducing myself. My name is Krishnaram Kentapati. I'm the Chief Scientist at Fiddler AI. So my background is in the areas like explainability, model monitoring, fairness, and privacy. So I've been part of Fiddler for a little less than a year, and before that, led responsible AI related topics at companies like Amazon's AWS machine learning and also LinkedIn AI team. Josh, would you like to introduce yourself?
Yeah, for sure. Hi, I'm Josh Rubin. Thank you guys all for joining us. I've been with Fiddler for about 3 years. I manage our data science team. My background was originally in physics, so I'm a physicist by training, but found my way out of physics and started learning machine learning for instrument calibration and signal processing problems, actually. And then gradually found my way into AI as a career and data science, and it's been a fun ride, especially with Fiddler so far.
Yeah. Thanks, Josh. So it's really exciting to talk about NLP and computer vision, right? Like we hear a lot about these topics of late, especially over the last 2 or 3 years. Let's start with a very basic question. What do we mean when we say NLP or CV models?
Yeah, so I think probably most people on the call can understand NLP to be natural language processing and CV to be computer vision. So at its simplest, we're talking about things like models that consume images or models that consume text as first-class inputs, as opposed to something that is more human feature engineered. So I think, as we've been thinking about these topics, I think an important distinction is the difference between human engineered features and things like NLP and CV that are more like the kinds of data inputs that humans encounter in the wild. And clearly we've entered the era in machine learning when not only can models consume these sorts of things, but all sorts of interesting multimodal inputs, text and tabular, text and image, sequential inputs, sequences of events. And so, there's exciting business advantages to be had. There's exciting data science challenges to responsibly using these models. But they offer different benefits and different challenges, or significant benefits and different challenges.
Yes, I think that's a great segue into the NLP and CV models. We'll kind of elaborate more and discuss more into this throughout today's conversation. Let's start with why are these models important in machine learning? Right? Why not just go with maybe as you were alluding to, like human engineered features over tabular data sets? Why are the NLP or CV models becoming important?
Yeah, so I think the key thing is that when we engineer features for models, very often we're summarizing information, right? We're somehow distilling a whole story, something complicated, into a few tabular fields or many tabular fields. And in the act of distillation, you're often throwing away sort of subtle semantics, contextual information. You might think about the transition between doing, natural language models with term frequency vectors, things like TF-IDF, where you count the occurrence of words in the absence of their, context and neighborhood, versus what we do now with, language models. Things like, a BERT model that you might use as a way to represent language, right? You it's, sophisticated and understands word position. It knows that, Apple computer is different from Apple the fruit, right? And as we've seen from things like these, large GPT-3 scale language models, like they're incredibly good at understanding nuance and context. And so, as we move to, there's important information that you run the risk of distilling away when we apply our human intuition to, characterizing in a very finite way. And machine learning has proven that, it needs less of our help than we may have originally thought. Assuming you have sufficient data to give it the experience to suss out those little nuances.
So maybe if you can add some example, like if you take computer vision, right? In the distant past, the researchers used to engineer features like maybe features that represent face or skeletal structure or eyes and so forth. And that required some way of mapping from the raw image to this kind of human curated features. But then what we have seen over the last decade or so is that the deep learning based models are very good at inferring subtle features that we may not even think of, right? Like, and that's why like we are moving away from human engineered features when it comes to highly unstructured data, like say text or images. So talking of large language models, like one of the things we are seeing of late is that there is a very large availability of unstructured data. So let's take finance as an example. We are seeing financial reports, 10K reports, earning call transcripts, various company filings, analyst reports, of course, like social media feed, right? Twitter and other feed. With so much data now, financial services companies are starting to adopt models which are multimodal, which take, of course, like the human curated tabular features, but at the same time also consume these variety of unstructured data. So by combining these two types of sources of data, they are seeing that there is improvement when it comes to, say, classification or sentiment analysis or extracting information and so forth. And that's one domain where we're starting more and more use of such large models, especially like large trained models, like large language models, or even language and image models. So let's see whether if there's interest and time, we'll get into that towards the end of the conversation. So with this context, so why is it important for organizations to, say, consider such unstructured models? Or rather, I think we kind of partly discussed that. What are the challenges companies face as they move towards NLP or CV models?
Yeah, so, certainly as a, representative fiddler, everyone, that we work with sort of, feel strongly that, this is the sort of, with great power comes great responsibility, right? That when you're dealing with unstructured data, making sure it's behaving as intended may become more challenging, right? If you're dealing with a simple logistic regression model on human, engineered features, there's lots of things that are fairly easy to keep track of for evaluating model performance. You run some accuracy numbers, you can look at, univariate histograms of inputs. Some things you might care about, though, in order to use your model responsibly are, is something changing in the real world, right? The world changes, COVID happens. That changes all sorts of things, right? That changes relationships that may be trained into models, the correspondence between the inputs and the outputs of your model. There may be, drifts in input features to the model. Your model may be, sort of resilient against those things, or maybe somewhat resilient against those things, depending on what your domain of your training data is. So, I think one thing that we've seen is that the problem of understanding, is my model still valid? Is it still making good decisions? What may be changing in its inputs? What may be changing in its outputs? How is its accuracy behaving? Those questions are much easier to keep track of in the context of, simple tabular models, to go back to the sort of more traditional human engineered features. When you start talking about things like distributions of text inputs, or something noisy happening. I hope you guys aren't picking that up too much. Or distributions of images and the ways that those can change, and how that may or may not be impacting the, underlying relationship of y given x that your model may be trying to reproduce. That gets more challenging. How do you understand a distribution of text inputs or image inputs or multimodal inputs? What does it mean to have a single data point that's a sequential input plus a tabular input plus a text prompt? So I would say, in addition to the sort of great benefits of incorporating data that's nuanced like this in this unstructured realm, it does get significantly more challenging to make sure that, not only from a kind of social responsibility perspective for high risk models, but also from a, kind of business bottom line perspective. How do I know that the world hasn't pushed my model into some regime where all of a sudden it's making a lot of predictions where it has no experience?
So yeah, that's a great point. I think so if you take, let's say a model for predicting financial returns, or a model for predicting maybe how different industries are going to perform, right? Like we not only care about how the model is performing as a whole, but also whether it's making good predictions for different industries, right? So that's the example where you're referring to perhaps like the business angle itself, right? Even when there are no regulations or social responsibility elements, even from a purely business angle, we want to understand how well the model does for different subgroups, right? And by figuring out the regions where the model is not working well, we can go maybe identify whether there are issues with the training data, whether the real world distribution has substantially changed for that segment, and go about mitigating those issues. And of course, like the social responsibility element is also an important, right? If the models are about, say, facial analysis, or even models for deciding whether to approve or deny credit cards, we want to make sure that the model works not only as a whole, but also for different demographic subgroups. It works well for different demographic subgroups, especially like even intersectional subgroups. So a little bit, we discussed a little bit about, say, monitoring of such models. Can you go into more on how would we think of monitoring, say, traditional tabular models, and how should we look at monitoring, let's say, NLP models differently? Like what are some of the challenges when it comes specifically to monitoring NLP models?
Yeah, so I think the sort of through line to modern ML models, and especially those that consume unstructured information, it's vectorization. It's that, and particularly around outputs of neural nets or deep learning models. It's that almost all of these models at some point through their processing stack, generate embedding or latent representations of information that can be multimodal, or, characterizes the information that they've consumed, the unstructured information that they've consumed, in some sort of nuanced way that preserves all of the relevant degrees of freedom in that information. So as opposed to the kind of crude thing a human might do when, or clever thing when feature engineering, the representation engineering that deep learning models do deep in their guts, you end up with a lower dimensional representation of that information. That's a vector that represents the relevant degrees of freedom of the problem that the models learned. And I think that's where, sort of the solution space lies for monitoring, right? It's instead of working in a space of text directly or a space of images directly, if you want model monitoring that's sort of sensitive to the model semantics, the nuances that the models learned, it seems to be that the best solution, at least the best one that I think I've heard so far, is that you want to keep track of distributions of vectors. And that's a sort of an approach that's applicable to a wide variety of models, CV models, NLP models, all sorts of heterogeneous, unstructured multimodal models. Almost always there is a vector distribution that can be monitored. And then it becomes a problem of, describing how the distribution of vectors are moving within some high dimensional space. I don't know if you want to comment on that. I'm happy to keep plowing along into, the key thing there is that, where you might, for a traditional model with, a traditional tabular model, the approach that we like are using, sort of information theoretic distributional comparisons. So basically functions that take, 2 histograms as inputs and output a number that represents the similarity of those 2 things. So, the one that we use most often is the Jensen-Shannon divergence, which is a symmetric measure that ranges between 0 and 1. And 0 means the 2 histograms are identical, and 1 means there's no counts in common bins. They're as different as they could be. As long as you can capture, partition your data into bins, you can use these distributional difference metrics to tell you if distributions are the same or different. And so, in a sense, there's a really nice extension of, sort of the traditional use of something like Jensen-Shannon divergence or PSI, the Population Stability Index. That's, super popular in the financial services industry. That's a very similar concept. If you can use those sort of regarded distributional difference metrics to compare histograms, they give you sensitivity to all sorts of differences that something like the average value wouldn't suss out. Symmetric changes in the distributions, for example. So if you can partition that high dimensional data, if you can bin it to bring it all back to the unstructured situation, if you can take an embedding or latent representation of data that's vectorizable and convert it to sort of a bin density estimate of one kind or another, that can be as simple as drawing some partitions in the high dimensional space. You can turn that into a histogram that you can apply these well-proven techniques to in order to track changes over time.
Just to comment on that, I think one key difference is when it comes to, say, tabular features, those bins are kind of pre-provided, right? If you take a feature like age, we can bin the age into maybe age 11 to 20, 21 to 30, and so on, and that gives us those bins automatically along with the feature. But when it comes to, say, high dimensional vector features like NLP embeddings or computer vision embeddings, now we have to come up with what those bins are, right? And that's where maybe different types of clustering or other approaches might potentially help towards that. All right, so let's kind of maybe go a little bit into the other type of challenges we discussed, which is about how to explain the behavior of such complex models. How do we go about, say, explaining NLP models or computer vision models?
Yeah, so I think Fiddler's taken a position that we're quite fond of integrated gradients and various variants of it as an explainability algorithm that works well for a wide variety of complex models. So if you're not familiar with the technique, integrated gradients asks the question of actually, Krishna Ram, are you getting a ton of noise from my microphone right now? There's some construction nearby.
No, I think it's fairly clear, so I don't hear.
Okay, good. Then I'll just
hear
continue.
your voice clearly.
Good. Thank you. Yeah, so the question of explainability, one approach to solving that is I should take a step back and talk about attribution methods, feature attribution. It's a question about on average, which features are driving a model to make a decision, to make a particular decision. You can look at these things in aggregate, or you can look at them one inference at a time. And one approach to answering that question, particularly if you have a model that has works in a continuous vector space, like neural networks tend to, is you look at the gradient of the prediction with respect to the various inputs. And all of our deep learning frameworks are happy to do backpropagation for us. And so that's not a big ask for those things to do. They can perform that efficiently. They can do it in parallel if you have the hardware to do it. And so the sort of simplistic approach is just to ask the question, in the region of the prediction at the explain point, what's the gradient of the prediction with respect to the inputs? Now, it turns out that models tend to make their decisions, they tend to be pretty consistent in their decisions in the region, in a reasonable region, and there's a ton of papers on this, but in a reasonable region around the explain point. And so
this is also related to these notions of robustness, right? If ideally we expect that if you perturb the input a little bit, tiny bit, the model's prediction should not change, right? So if the model is designed to be sufficiently robust to such tiny perturbations, then when you take the gradient, you would not see much of a difference over there.
That's right. You're sitting on sort of a plateau in the high dimensional space, of the plateau of the prediction surface. And so integrated gradients essentially, compares a baseline point, some sort of counterfactual that's typically a kind of uninteresting comparison point to the point where your model's making a prediction. And it steps through the high dimensional space. And it adds up little pieces of gradients as it goes. So it's a kind of you do it like a path integral through the high dimensional space. You tally up the gradients, and it tends to provide a very efficient way to explain down to your input features. And those features can be as granular as pixels in the CV case. They can be token level in the language case, but to bring it back to this kind of embedding continuous vector representation concept, the integrated gradients explanation method works on vector distributions, or works on vector on a vector space. And so there's always a little bit of a game to, how do you translate that back, if you're talking about natural language, to the original token space, where you've gone through some sort of embedding layer that's not continuous, not differentiable through. And then this family of attribution methods has this sort of interesting property that feature attributions can be added together, sort of additive attribution methods, and you can group them in that way. And so what that means is, in the CV case, you have a lot of power to do things like pooling, and look at superpixels in the input space, and that provides a much more human grokkable understanding of what macroscopic combinations of pixels are responsible for driving models. In a language case, that can you can, if you're working with a BERT model, you might be familiar with the word piece tokenizers that BERT uses, where it breaks words up into tiny little fragments. Then you can regroup those into human level kind of meaningful semantic chunks.
Yeah, for instance, like in the case of NLP, right? This could be maybe phrases, sentences, or even potentially paragraphs, right? We could think of each paragraph as a unit and look at which paragraphs contributed the most to the model. Or in the case of maybe computer vision, right? If needed, we could even leverage domain-specific knowledge, right? Like maybe segmentation techniques, and treat each segment as like a super pixel, if you may. So I see a lot of interesting questions coming from the attendees. So let me start with one question, which is, if the vectorized feature distribution changes, what should we do? Should we retrain the model? Do we need to adjust the sentence to do vector transfer process? I'm not fully sure what it means, but I think the spirit of the question is, when the feature distribution changes for such vector-based techniques, what should we go about doing then?
Yeah, so for me, that's if you're responsible for the model, if you're in ML operations, or you're a model developer, or a data scientist who's responsible for a model, I think a shift in a feature distribution, one that's statistically significant and sort of a size that is, you care about. There's some application specific decisions you need to make there about when you might, what's the threshold of concern. But I would say a feature drift is, an opportunity to pay attention. That's sort of your call to arms, that you might want to try to understand why the features are drifting. There might be a cue that you should, gather some data labels. Maybe you get some data labeled and you go and you run it if you don't already have ground truth available or actuals available for your model. It would be a good time to verify that the model is performing with, the accuracy as trained, expected accuracy. So I suppose that's one piece. I'm trying to think. I had another thought in the course of that. Yeah, and then the other thing to do is to try to understand something about, what may have changed in that drifted distribution. There are tools for, so one thing, in Fiddler's approach to this problem, as I alluded to, we try to break up this high dimensional distribution of vectors into bins by partitioning the data. You can ask questions like, in this time interval, are there any outliers in this bin, outside the realm of what we saw when we calibrated this partitioning on training data? So far in our experiments, that's served really well to identify, new kinds of data that might have crept in that weren't in the training distribution. So we've seen that it worked actually incredibly well in a recent computer vision case on side scan sonar, where there were new kinds of images that were introduced that were distorted, or pictures of broken objects, either electronically distorted, or the subjects of the images were fragmented, and looking for outliers in those within those bins, within the bin assignments, isolated those quickly. Another thing to do is look at dimensionality reduction and try to unfold that high dimensional data into a more human grokkable interpretation using manifold learning techniques like UMAP, and trying to identify where new data may not be following the pattern of the old data in the high dimensional space. So you have a couple of tools. You might encounter something there that is different than your training data, where your training assumptions have been stressed in some way or violated in some way. And then as a model developer, you can make an informed decision based on your application for whether that's something that needs to be remediated, whether there's some sort of risk associated with this new kind of data that's wandered into your distribution.
So there is a, so I see a kind of related follow-up question to that, which is that i- is it enough to just monitor the distribution of the embedding vectors? Why not also monitor the distribution of the model predictions themselves, right? I think we are not saying that we should not monitor the model predictions, right? But in fact, it's always desirable to, the ideal goal is like, if you can monitor the performance of the model directly, right? Monitor the accuracy or AUC or other metrics of the model. But the reality is that in almost nearly all practical application settings, you don't have access to a ground truth in near real time. So you kind of go for proxies. One proxy is, as this question suggests, maybe monitoring the distribution of the model predictions, whether that is changing. That's important. In fact, in Fiddler, that's something that we support as a first-class citizen. Then the next step is, like, if those distributions are changing, what's responsible for those? I think that's where looking at the distribution of the underlying features, in this case, the embeddings, plays a big part. It's all this is more around diagnosing the root cause, right? Like analyzing why these changes are happening. Should we worry about these changes, or is it something they're kind of benign changes? So let me go to a different question, which is, does Fiddler generate its own embeddings on our data, or do we need to send the embeddings we have learned while as part of model training to Fiddler to measure the drift?
Yeah, that's a super question. We've just released our very first cut of, I don't know if we outwardly call it vector monitoring, but that's the underlying feature that drives both the CV and the NLP monitoring that we provide. And in our first cut, there is, we don't do any embeddings for you. It's your responsibility to take your NLP, and you can, send it to TF-IDF if you want to do something simple. You can use Word2Vec. You can use BERT for embedding. Possibly the more interesting, so the simple answer to your question is, today, you bring your own and you do something that makes sense to you for your use case. If there's a lot of demand, we've certainly considered providing mechanisms for some standard transformations. So we could provide, and I think it's not clear exactly what we would choose for that, but we might provide something like, inbuilt BERT embeddings or something if people just want to provide, text input. Their model has pure text going in. For scenarios where users have, are both monitoring and explainability users inside of Fiddler, you may have ingested your own model into the platform for explainability purposes. And your model may take text as an input. We provide a mechanism to either allow embeddings to be regarded by the platform as model inputs or metadata. So if you have a model that's taking in text, you can also supply embeddings as metadata. So they're not regarded as input features. In some scenarios, you don't have a model in Fiddler, and you may want to provide the embedding components as the model inputs, in which case the raw text can be provided as metadata to provide the ability to kind of drill into that. It's embedding components are great for doing drift monitoring, but not great for surfacing what's going on to humans. So you always want to be able to trace, if you have outliers detected or something like that, you want to be able to trace it back to the raw text that caused that embedding. But the simple answer is, today you bring your own. And I did want to mention that I think the most interesting use case is if you're working with a deep learning model, you can bring whatever representation your model has learned that's most appropriate for the task you're trying to solve. So that's super powerful, right? Because your model has learned an optimized internal representation for the vector distribution. It may have more than one. I mean, one thing we've seen is that, the representations of your text or CV or whatever your unstructured data is, as they move through a deep learning model, can represent different kinds of semantics that you might care about. And some of those representations may be more like early warnings. You can see drift there before you start to see a swing in performance. And I think even on our side, we're, kind of at the beginning of the journey of understanding like what makes the most sense from the perspective of, what kinds of representations you monitor. So yeah, it's bring your own today. If there's a lot of demand for something automatic, that'll follow shortly.
Just to add to that, I think one benefit of bring your own is that, as John mentioned, depending on the specific application setting, you may use different ways of generating the embeddings, right? Or it could even be specific to the application task at hand. And if that's the case, it's perhaps best to monitor those embeddings rather than an off-the-shelf way of generating the embeddings. So yeah, again, like on the topic of embeddings, so I see a question which is, what does drift mean in NLP setting? Like, can you give examples of NLP use cases? So it seems more natural or intuitive in the CV setting. You gave this example of the sonar images, right? What's an analog in the NLP setting?
Yeah, I mean, one example that our colleagues at Arise like to use is, what happens if you've trained a model on English and you end up with a bunch of, Spanish text in your production setting that enters into your model. That's something you'd like to, a pretty like brazen out of distribution change that you'd like to know about. But I think there are more subtle examples, right? There's changes in vocabulary over time. So I was just talking, it was an interesting conversation yesterday. We were discussing things that might have changed during COVID, right? And I can't, so I have to, with the disclaimer that I'm not a physician and don't really know, sort of speaking way outside of my expertise, but you could imagine that, as we started to learn what COVID was, that the way that symptoms were represented in doctors' notes about, exams might have changed in subtle or not so subtle ways, right? Like at first you might, you didn't know you were looking for COVID. You didn't know that was a likely diagnosis. Once we really started to know what COVID was, and there was a high throughput of, patients who all had the same symptoms showing, it strikes me that it could have been entirely possible that the way that those cases were written are different than before we knew a lot about COVID and its symptoms and what was going on with the pandemic. So, there can be subtle things in the way that vocabulary changes over time. Another example in NLP, one of the test cases we played with when we were prototyping the feature, our vector monitoring feature, was looking at news headlines. So there's an amazing data set from the Australian Broadcasting Company of 20 years of news headlines. And there's like, I don't know, hundreds of thousands of headlines over time that they have in this data set. And there are trends in the kinds of topics that are covered in, as time passes, right? There are political cycles, there's wars that happen, there's international events, there's topics that become popular and then become uninteresting, right? So, over time, there can be all manner of interesting kind of semantic changes in how, the different distributions of topics and how language is used. And all of that can impact how well your model is performing, depending on its task.
So also, like, I think, so we briefly touched upon two broad types of changes, right? One is that COVID is a great example where the real world itself changed. The way things were written, maybe at the beginning of the pandemic or before the pandemic, versus how they were, this diagnosis was written a few months later, could be very different. The other one that happens often is the out of distribution thing. The model may have been trained on some population, but once it's deployed in the wild, invariably the model gets used by a population which differs a little bit from the distribution on which it is trained, partly because we may not anticipate where maybe the model is going to get applied, right? Like in ways that the model developer or the company may not have anticipated. Let's think of, say, sentiment detection. There are studies that show that even if you take tweets, the way tweets are written, let's take tweets in English itself, the way tweets are written by people from different ethnic backgrounds or communities may have slight differences. So a model that works well when applied over, say, tweets from one community may not work as well over another community. Josh, do you want to just read the next questions? There's some construction happening. I hear a lot of noise at my end.
Oh, so I'm actually struggling to figure out where the questions are popping out. Maybe you can guide me towards.
Okay, so
I see the chat, but I don't see the questions there.
It's in the Q&A tab. Let me read the next question for you.
Sure, sorry about that.
If you're using pre-trained models or transfer learning, what will drift look like?
Oh, geez, that's a tricky question. Well, I think for monitoring, I think generally this topic of vector monitoring, it applies to the input space of your model, right? It's what the distribution of text is going in, whether it's a pre-trained model or a transfer learned model. I think this notion of monitoring vector distributions at different stages is interesting. So, one thing you might choose to do is look at a Word Devec, create a sort of a, so within the Fiddler product, we call the vector monitoring, we call it a custom feature. So there's a concept of a custom feature that you create based on vectors, some set of vector components. And you can create more than one from the same components. So, geez, all sorts of noisy things. So one thing one could do is, create a custom vector monitoring feature based on, you got to tell me again, Krishna Ram, if I'm getting a lot of noise. I might actually jump over and
no, I don't hear any noise. I think it seems perfectly fine.
Yeah. Hang on, I'm going to switch one thing. Bear with me for 10 seconds. Thanks for bearing with me, folks. Yeah, there was one very
yeah, we don't hear any noises, Josh. Do you hear anything from my end?
Nope. Oh, noise
fantastic.
cancellation is great, but it had reached the threshold where it got hard to talk. Yeah. So yeah, we were talking about right. So either pre-trained model or transfer learning, right? So we've played out this transfer learning use case. It turns out that, and when I was mentioning before, certain representations acting like early warnings that something's changing, you might monitor the output, if you're talking about using transfer learning in the context where you're retraining or bolting on some subsequent classification layers onto a pre-trained model. It's both interesting, the general features, the general vector representation that comes out of the pre-trained part, and also the more semantically specific pieces that are captured by your sort of transfer learned piece. So, one thing we've experimented with is monitoring, setting up multiple custom features at different stages to provide alerts on different kinds of things. So, I think we'll have sort of clearer guidance as time goes by. But I think, in the absence of a more specific prescription, I think monitoring more things and getting alerts on more kinds of drift is better. Better, best be kind of over prepared, I guess.
Sounds good. So let me move to the next question. Could we do model monitoring alone, or do we need both model monitoring and explainability together?
Yeah, within Fiddler, I don't know if that's a question about our product or a question about, in general, whether, you know, I
So
think
I would interpret that as in general. Let's kind of discuss in general.
Right. So I think we regard both of those as important parts of, you know, responsible AI, but they play somewhat different roles. You know, the explainability piece, and you know, it depends somewhat on, you know, who your stakeholders are, what your model validation scenario is. You know, there are lots of reasons why you might want to be able to understand, you know, quote unquote, the reasoning of the model for a particular inference. But I don't know that in every scenario it's necessary. So in high risk models, you know, I mean, you know, for example, financial services, I don't know, you know, there's regulatory requirements on, you know, being able to explain the explanation, being able to explain model predictions. There's, you know, essentially an audit process for certain kinds of models needs to be in place to be able to go back and review predictions. You know, I think there are also lots of scenarios where there are stakeholders who aren't machine learning specialists who are consuming predictions, who can benefit from, you know, understanding the why behind model predictions. So this is kind of the human in the loop use case, right? This could be a lending agent at a bank. It could be a career counseling persona at a talent placement company who's consuming machine learning predictions in order to, you know, help make recommendations for how someone develops their career. It could be a physician who is using some machine learning predictions to, you know, make care decisions, right? If you can give those domain experts the why, they're able to do their job more efficiently because the computer never gets tired. They're able to not miss important details. And they're better able to communicate with model developers in areas where the model is reasoning in a way that's inconsistent with their domain expertise. So, you know, I would say that explainability component, you know, whether it's necessary and to what degree depends a lot on your use case and who your stakeholders are. I think there's a lot of scenarios where having explainability available is important. I would say that the model monitoring is more like a necessity for operating a model in production. You know, if there is any sort of harm that can be created by your model wandering off into a region of its, you know, feature space where it's not appropriately constrained, or there's anything in the universe that can change that, you know, causes for example, a concept drift, a change in the relationship between the inputs and the outputs that your model might not be prepared for in a way that has a business cost to you or some sort of a risk. It's really critical that you have instrumentation on your model in order to understand whether, you know, you're subject to changing conditions of one kind or another.
So just to add to what Josh said, so as Josh alluded to, like monitoring is clearly table stakes, right? I think there is no disagreement on that, and we are kind of moving. Even when we talk to customers, we are sensing that compared to a year or two back, customers now realize the importance of monitoring, right? The monitoring is often directly tied to business impact or revenue or profit or other business metrics. Explainability is helpful during, say, even debugging. When something changes during monitoring, now to go and understand, is this something that we need to worry about or is this benign, right? I think explainability plays a huge role there. In addition, explainability also helps for the data scientists themselves, like when it comes to, say, how to design maybe better features, right? If in the case of, say, multimodal models, right, understanding which of the tabular features are important, it can help in figuring out, should I go and maybe collect more such features? Should I develop more such similar features? Or should I develop some orthogonal features that may contribute more to the model? Like even to understand and improve the model over time, explainability plays a huge role. And the closely related aspect is in domains which are heavily regulated, explainability can play a big role in understanding whether the model has any biases as well, right? Or
like for instance, if you notice that some feature is being given disproportionately high weight compared to what our domain intuition or expertise would suggest, that may be a cause for concern, right? And especially all the more if that feature is somewhat partially correlated with gender, race, or other demographic attributes. So all right, so let's move on to another question, which is, I'll kind of maybe read two questions together. So one question is about if there is a drift in, say, setting like camera shifts, which affects the model performance, how should we handle such drifts during inference? Is model retraining the only approach, or is there something else? Yeah, a related question is, should there be a tolerance limit or range for drift? Let's say a model has been trained to recognize maple leaves and then it's tested with a plantain leaf. Will the model be able to generalize, or do we expect the model to fail miserably?
Yeah, that's an interesting question, and a good one. So there are a few pieces here. So I can't speak to whether your model will fail miserably and what its resilience is like with respect to, I mean, the example you raise is a question of seasonality. You know, so there are different kinds of things that can happen in our data sets, right? Over time, there are cyclic changes. Those are the sort of seasonality components. I can tell you today, Fiddler doesn't directly try to compensate or accommodate seasonality. And so the best advice I think we have is either you set a tolerance that accepts seasonality, or you monitor your data on a time scale. I mean, one kind of seasonality is a day-night cycle, right? People send more text messages during the day, for example. You know, if you monitor data that is, you know, kind of on time intervals that integrate over cyclic behavior, that's one way to sort of, you know, factor that out of the analysis. There are, you know, I would say, you know, there's a question of setting thresholds on these drift metrics. Like, where do you want an alert? Where do you want to start caring? So that's the other end of the problem. Like, one is like, how do you deal with seasonality? I think in the future, probably we'll have a better approach for factoring seasonality in, but you know, I've given you a couple of ideas so far. You know, but there is a question of like, how significant a shift do I care about? And I think this is a place where it requires some, you know, domain knowledge for what the problem is you're trying to solve. And probably as a model developer or a, you know, data scientist, MLE, analyst, whatever your job is, statistician, you know, you need to know something about your model's training set and resilience. So there is a component of bringing your own knowledge, but you know, the Jensen-Shannon divergence and the other drift metrics that we talk about, you know, I think the best thing you can do is determine a kind of threshold on the basis of how much distributional shift do I care about? You know, try to quantify that in some terms that, you know, make sense for your use case. Maybe that's like, I care if the mean shifts 5%, and my distribution looks something like this. You know, in those scenarios, that's enough to constrain a value of the Jensen-Shannon divergence. So you can place a threshold in a kind of mindful, application-specific way to try to ignore the kinds of typical variation that you'd see. And then the one other aspect to that is, and something that I think we're getting better at as a product is understanding, you know, how to interpret the statistical uncertainty that's associated with distributional drift metrics. They have this funny characteristic that when you have, you know, not so many statistics, when your statistics are low in a bin, the Jensen-Shannon divergence, because it's asymmetric, moves up. So it sort of manifests its statistical uncertainty as a sort of a noise floor on the minimum effect size you can resolve in a given bin. That's a function of how many events fell into the bin. So, you know, understanding that clearly, setting an appropriate threshold, and then trying to factor in seasonality effects into the bin, the scale of the bin that you look at can help address some of those questions. That's a very good question.
Sounds great. We are coming close to the end of the webinar. So at the beginning, we promised that we will briefly touch upon large language models, or more broadly, large trained models. So I thought I'll just maybe leave some thoughts for the attendees to reflect on. Some of the very interesting and fascinating trends that are happening in this domain. So for one, we are seeing a move towards models which are zero-shot task generalization models, right? Like the models like T0 from Hugging Face, where the same model is able to accomplish several different tasks, ranging from sentiment analysis, Q&A, reordering words in a sentence, sentence completion, and so forth, based on the prompt of the user, right? Now, that brings up an interesting research question or a practical challenge. How do we go about monitoring such models, right? What does monitoring even mean in a setting where the same model is accomplishing a variety of tasks, ranging from classification to maybe just a free-form text generation? The other thought is, with such models, how robust are they? Like when I just played with the T0 model myself, I noticed that for the suggested example, the model works great, but if you modify the prompt a little bit, it's fairly easy to fool the model, right? Where the model does not make the correct prediction in terms of a relationship or any other task at hand. Yet another dimension that's kind of interesting in this setting is when it comes to explanation. Like, how do we go about explaining the text generated by such large language models? We're seeing a few recent trends. There is a very interesting line of research called chain of thought prompting. The idea is take a model like, say, GPT-3 or PaLM or any other model, and instead of just asking a question, so if you provide a chain of reasoning, right, especially if it is a math problem solving, word problem solving, if you provide a chain of reasoning, then the model is much better at learning that chain of reasoning, and it's able to provide a similar reasoning to arrive at the right answer. So one can even think of such models as models which are perhaps not only generating model output, but maybe trying to also provide associated explanation of the output. So in general, I would encourage all of you to take a look at what's happening in this domain. And we don't have time to go into the domain of both the language and image models together, right? Whether it is DALL-E 2 or Stable Diffusion, and so forth. So that brings us close to the end of the webinar. Josh, would you like to maybe share some closing thoughts, and maybe just reflect on how you moved from being a physics PhD researcher to data science and computer science?
Oh yeah, I was maybe going to handle that one offline. It's a combination of having colleagues in industry and a few connections to get a foot in the door for a problem that I could solve with a skill set where they needed someone. So there was some luck there, but also there's some really great sort of fellowship programs. So I went through there's a program called Insight Data Science that I'm not sure they were struggling a little bit during the pandemic, but they basically take people with quantitative science backgrounds and help them learn the right jargon for to be data scientists and machine learning engineers and find roles. So I think there are programs like that that can be really useful in building a network. So I think I'll follow up with Al about that question offline, but there are a variety of things you can do. And then the other question, I guess, was for kind of parting thoughts. So I'm going to just cut to I have a little list of notes that I made right before this. If I had to kind of wrap what we wanted to talk about here in kind of 4 points, I'd say, unstructured data, it encodes important context and semantic nuance. and that can get lost in human dimensional feature or human engineered features. Second is those features are valuable. I mean, we've seen them be worth millions of dollars in the financial services context. Like it's no joke that there's valuable information to unlock in unstructured data. Vectors are your key to working with unstructured data as inputs. That's CV, NLP, and also all manner of kind of multimodal models. And then I think we see responsible AI as a combination of this kind of table stakes model monitoring that includes this kind of vector monitoring for these complex cases, and then also explainability, particularly where the task and stakeholders can benefit from that. So I think those were the things that we wanted to touch on. So I'll call those takeaways.
Wonderful. Thanks.
Right.
Thanks, Josh, and thank you all for attending today's webinar, and for those watching the recording afterwards as well. And please feel free to reach out to any of us if you have more questions or thoughts or comments.